Hello there. In this lesson, we're going to learn about combustion. So I found a few pictures that I had about things burning, which is combustion. This here is a candle, of course. And here was a little experiment I was doing with a lump of sugar on a pile of sand. And so both of those being combustion involve some recognizable traits, right? You get this nice bright flame, different colors in these cases. And you can imagine there's some heat given off by that as well. So that's what we're going to be looking at in this lesson. So you can have combustion with a variety of things. The main components have to be that there's some sort of fuel and it has to react with oxygen. And that reaction then has to give off energy, that is the heat and the light that we observe. So the two that we're going to look at are the combustion of elements, where they react with oxygen. We've already seen a couple of those. And the other one is hydrocarbons, which we'll get to, which are the main fuels that you see around you. This here is an image of the Hindenburg disaster. And they used to make these lighter than air ships where people would ride around underneath them. But they filled them with hydrogen, which is super dangerous, as you can see. And of course, that can combust and burn with oxygen in the air, and that's what caused the big disaster there. Here, you're just using paper and wood as a fuel, and oxygen as well, and that's what's going to produce that combustion. So we'll start with element combustion. This here is a little piece or strip of magnesium metal, and if you heat it up enough, it gives off a super bright light that you might have seen in class. And told not to look directly at it because it can harm your retina to some extent. And but it is really cool, and you end up kind of looking like Harry Potter if you're the one holding the metal as it burns. And it's reacting with oxygen in the air, and you're going to produce an oxide when you're done. So that's combustion, just as a synthesis reaction as well, sort of two classifications in one. As far as equations go for combustion of an element, if it's the magnesium and you're adding the oxygen in there with some heat, obviously, you're going to end up with magnesium oxide. Both of those have a charge of +2 and -2, and it'll be a solid. And to balance that out, you would need 2 there and 2 here. For the Hindenburg, it was hydrogen, and it reacts with oxygen as well. These are both gases, and you end up producing, surprise, surprise, water. And the same balance will be needed here. The second type of combustion we're going to look at involves hydrocarbons. So I looked through my pictures and I found hydrocarbons from around my home and likely your home too. This here is propane. This is at the gas station, and you can see on here there's octane. In here you have hydrocarbons as well. And the difference between all these is just the number of carbons in the molecule. So they're all molecules that have hydrogen and carbon, as the name suggests. Propane, the prop stands for 3, so you end up with 3 carbons and 8 hydrogens. Octane, as you probably deduced, has 8 carbons and 18 hydrogens. Baby oil, I looked this one up, and the average number of carbons in there is about 15. So you can see the bigger the molecule, the more condensed or more solid your substance will be. And this will have 32 hydrogens. And then in petroleum jelly, what you end up with is an even bigger molecule with about 25 carbons. Apparently is a bit of a range, but that's the average. And then you would need about 52 hydrogens to go with that. So those are all hydrocarbons, and they'll all burn if you give them enough heat and oxygen. Away they'll go. And so that's the type of combustion that we're going to look at to finish up here. Alrighty, so the products of hydrocarbon combustion are going to be carbon dioxide. So the carbon part of the hydrocarbon makes carbon dioxide. And the hydrogen part makes water. So we end up with those two products, CO2 and H2O. And the bigger the molecule, the more of those products you'll get. So in this case, we've got 3 carbons, so we're going to need 3 carbon dioxides. We have 8 hydrogens, so we're going to get 4 waters. 3 times 2 is 6, plus another 4 makes 10. And so I'm going to need 5 oxygens to balance that out. Carbon dioxide is a gas. Water, of course, is a liquid. Same thing here. This is octane. And we got CO2 as well as a product, and water. There'll just be a lot more of these. So we need 8 CO2s, and we're going to need 9 of these waters, and that's going to give us an odd number, so we're going to have to use our doubling trick. So I'll use a different color here. We'll double everything. We'll make this 2, make this 16, make this 18. Now 16 times 2 is 32, plus 18 is 50. So that means we need 25 oxygens. So there you go, nice even numbers. Now you may have seen flames burning where there's a lot of black sooty smoke coming off of it, or a really yellowy flame that isn't burning very efficiently. And this is because there is not enough oxygen available to completely react with the hydrocarbon. And so in that case, you're going to get some leftover bits. So there's a bunch of leftover bits that are possible, but the 2 that we're going to look at are just some plain soot, which can be as simple as just carbon atoms that are left over and unreacted. And another one that's very dangerous is carbon monoxide. Carbon monoxide is poisonous to us because it's very similar in structure to oxygen and can be taken up by the proteins in your blood that carry the oxygen and essentially kind of suffocate you. So the carbon we're going to represent for the soot, we'll represent that as carbon as a solid, and carbon monoxide is a gas. So here are a couple examples of incomplete combustion equations. If you remember from the previous balancing we did with complete combustion, with the propane here we needed 5 oxygens and we only have 3. So that means we're going to have different products in order to satisfy that limited number of oxygens. So we'll start with the hydrogen here. We have 8 hydrogens. All the hydrogens are in this water, so we're going to have to use them all up there. So we're going to need 4 of those. So that uses up 4 of the oxygens, and we have a total of 6, because 3 O2s gives us 6. So that means we got 2 left. So for these 3 carbons, we can only make 2 carbon monoxides. That uses up all the oxygen that we have, and that leaves us with 1 carbon left over, which is our soot. Now for this octane down here, we're going to use 8 oxygens. We really shouldn't have 12.5 to completely combust this, but we have 16, so we'll make do. So first off, we're going to use up what we need for our waters. So that means we need 9. So 9 out of the 16 have been used up. So that means we've got 7 left. We can use 3 of them here if we want. So 3 times 2, that'd be 6. And we still have 1 oxygen left. And we can put it there. So we'd get 1 carbon monoxide. That uses up all the rest of the oxygen. And that still leaves us with 4 more carbons as soot. So with these incomplete combustions, there is a variety of ways to balance them. I didn't have to balance with 3 here. I could have moved this around. In fact, let's do that. A second balance we could have done with the carbon dioxide and the carbon monoxide and the carbon here is it could have done 2 here, and that would have used up only 4 of the remaining 7 oxygens, which means we'd have 3 left, and we could have done 3 carbon monoxides here. And then, so that's total 5, and then we would have needed 6, 7, 8 for the remainder. So that would have been another balance that would have been equally valid. And honestly, it's going to be a big mix of things. It won't be a consistent ratio whenever you have incomplete combustion.